Good day and welcome back to the second part of our discussion of triple integrals and cylindrical coordinates. So I want to pick up precisely where we left off in the previous video. We introduced the idea of a cylindrical coordinate system that would be polar coordinates in the xy plane with a third dimension added in. And cylindrical coordinates, as we saw, are well suited for describing cylinders and cones. So when we encounter solids of integration that involve cylinders and or cones, it now just becomes a part of our thought process to think, will cylindrical coordinates apply? And leads nicely into our topic of discussion, how do we apply cylindrical coordinates to a triple integral? So for example, if we are to start off with this solid E described above, how do we set up a triple integral in cylindrical coordinates over E? And kind of the nice thing is, remember, our starting point is essentially always the same. We have an outside double integral and an inside single integral. And we're going to look at this solid as varying in the z direction. And what we are told is that in the z direction it varies between a smaller surface given by u1 and a larger surface given by u2. So we're thinking on the top, we have this larger surface, u2 of xy, and on the bottom, we have this smaller surface given by u1 of x and y. So in the z direction, we can see that our solid is going to vary nicely between this smaller surface, u1, until we hit this upper surface, u2. So on our inside limits of integration, we are going to be integrating from z equals u1, the smaller surface, to z equals u2, the upper surface. And note at this point we have done nothing new. This is the exact same approach we would have used in our previous section when we were setting up triple integrals. The new part is that we are now going to convert that outside region of integration D so that it involves polar coordinates. And we're going to make the assumption that D is one of these polar rectangles. So I should have mentioned this previously. Let's say that D is described to have R values varying from A to B and theta values varying from alpha to beta. So alpha would be kind of the smaller theta value, beta would be the larger, and the inside portion of D would be R equals A, and the outside portion of D would be given by R equals B. And essentially what we need to do is take our triple integral and just convert everything in terms of polar coordinates for x and y and leave the z as it is. So note, each x is going to become an r cosine theta, each y becomes an r sine theta, and z remains the same. So in terms of limits of integration, we go from u1 of r cosine, r sine, up to u2 of r cosine, r sine. And remember, this is the most general possible version, so this is going to, of course, look rather complicated and abstract. In a concrete example, as we'll encounter in a few minutes, we'll have very nice functions that we're working with, and it will look, I hope, substantially better. Because we are going into polar coordinates with this dA, it's going to become r dr d theta. So note the dA becomes r dr d theta as it did in polar coordinates, and then we add those limits of integration. R in the middle we said is varying from A to B, and theta on the outside from alpha to beta. And to summarize as efficiently as possible, we are essentially using polar coordinates in terms of x and y and leaving z as is. So let's investigate a nice concrete example. For the given example, we are asked to evaluate a triple integral and we're given a description of the solid E, which we'll be integrating over. And this is a very standard type of example that we will be encountering. And based upon the description we have of the solid E, or potentially the function we are integrating, we somehow want to decide which coordinate system to use. And at this point we have two choices, Cartesian or now cylindrical. The first step towards doing so is to sketch the solid of integration. We are above the z equals 0 plane, so sitting above the xy coordinate plane. We are below z squared equals 4x squared plus 4y squared, and inside this cylinder, x squared plus y squared equals 1. So it's important to be able to quickly and efficiently identify the surfaces that bound our solid of integration. So looking at this remaining surface, I want you to take a moment and describe this surface with one word. And if you said cone, I agree. Note, we can write this as z squared equals 4 times x squared plus y squared. And if we wanted to think about converting this into cylindrical coordinates, just for fun, we could rewrite this as z equals 2r. So let's go ahead and sketch this solid. We have a cylinder of radius 1 wrapping around the z-axis. And remember, we're above z equals 0. And this is something that, note, we can very conveniently describe in cylindrical coordinates. In cylindrical coordinates, this becomes r equals 1. But we're also lying below a cone. So if we wanted to include the sketch of the cone, it's opening up around the z-axis. And remember, our picture does not need to be perfect. Far from it, it just has to get that general idea and shape across. So I'm going to erase a few extraneous lines, and we can now hopefully much more clearly see a picture of our solid E. We are below the cone and we are inside this cylinder. So it looks as though we have a cylinder and we've hollowed out this kind of conical shape from the top, which as a solid of integration is highly conducive to using cylindrical coordinates because it only involves cylinders and cones. So let's go ahead and see if we can convert our triple integral into cylindrical coordinates, and then while we're at it, we will evaluate as well. The triple integral over E of x squared. So note our starting point is identical to what it was previously. We're going to view this as varying in that z direction. You vary from z equals 0 up to where you hit that cone. So in the inside integral is going to be in terms of z, and we're integrating from z equals 0 up to the cone. So that cone would be given by the square root of 4x squared plus 4y squared if you were to isolate it so that it's in this form z equals. Now is the new part where we go ahead and convert this into cylindrical coordinates. And before doing so, I'm going to sketch our region D in a separate coordinate system. And we can very clearly see our region D above as being the region bounded in the xy plane by a circle of radius 1. So maybe we would say descriptively a disk of radius 1 centered at the origin, which is easily describable in terms of polar coordinates. Our r values vary from 0 to 1, and we're going all the way around, so the theta values are varying from 0 to 2 pi. So let's now convert into cylindrical coordinates. Remember, the dA is going to become r dr d theta. And you can leave the r outside of the dz, or you can move it inside the dz, whatever your preference might be. Now, when we convert into cylindrical coordinates, we leave each and every z unchanged, but every x and y gets converted into polar coordinates. So the first thing we might notice is our integrand is x squared. So x is r cosine theta. So we would have r squared cosine squared theta. We're integrating on the inside from z equals 0 up to the cylinder. But note, we already described the cylinder in cylindrical coordinates as z equals 2r. And then on the outside, the order is irrelevant because we're integrating over a polar rectangle. We have dr d theta. So in the middle, we go from 0 to 1 in r, and then 0 to 2 pi in terms of theta. And I would consider getting to this point to be really the new part of the problem. But I'd also throw out there, if you look at the final example from the previous section, we actually were using cylindrical coordinates without knowing it because it's such an intuitive thing to convert that outside double integral into polar coordinates. So let's go ahead and evaluate. The first thing we need to do is integrate on the inside. And note on our inside integral, the integrand, r cubed cosine squared, is a constant with respect to z. So we get that constant multiplied by z, and we're evaluating from z equals 0 to z equals 2r. So we substitute in z equals 2r minus sign, substitute in z equals 0. Now note, when you substitute in z equals 0, you get back 0, so we would be left with a 2r to the 4th times cosine squared theta, which is a very familiar double integral. Note, it's the ideal scenario. We have limits of integration, which are all constants, and our integrand function separates into a function of r times a function of theta. So we could make this a single integral over r multiplied by a single integral of theta. Taking care of what might be the simpler one first, we would have 2/5 r to the 5th from 0 to 1, which gives us back 2/5. Secondly, to integrate cosine squared, which is something we've done several times recently and hopefully is becoming almost second nature, we rewrite it in terms of that double angle formula. So cosine squared theta is 1/2 the quantity 1 plus cosine of 2 theta. Once we've rewritten it, it becomes much simpler for us to evaluate the integral. The antiderivative of 1 is theta, and the antiderivative of cosine of 2 theta is 1/2 of 2 theta. Noting a few cancellations, the squares go away, and when we substitute in 2 pi and 0 for theta, note every single term will be 0 except for when 2 pi goes in for theta, because sine of 4 pi is 0, sine of 0 is 0, and 0 is 0. So I will let you work out in extra detail if you need to, but note what we will end up with is the 1/5 out front multiplied by 2 pi, which completes our first example of a triple integral in cylindrical coordinates. We will investigate one more such example in the next video. So stay tuned and take care.